Now as I told you about the differential law equation, you know that, but like we are going to start with a new topic, that is the molecularity, and before that I am just recalling that differential law equation. So you know that suppose I have this reaction, A moles of A react with B moles of B and give rise to C moles of C and D moles of D, right? You know that. If I need to write the rate of reaction in terms of differential rate law equation, how I'll write? Tell. So you also write in your copies. So we'll be writing in this way, that rate is equal to K, rate constant. These are reactants, right? So I'll be writing the concentration of A into concentration of B, and we have this X and Y, where I told you this X and Y can be equal to A or B, or cannot be, may not be equal to A and B, because these X and Y are experimental values, not the stoichiometric coefficients, right? So in this reaction, like I just want to explain you that, like when you did few examples, what you get to see, like in some of the reactions this X and Y was equal to A and B, and in few reactions what we get to see that these X and Y were not equal to A and B, or you can say they were entirely different. Now what is the reason that these experimental values are not matching the stoichiometric coefficients? What is the reason behind that? So my question today in this topic is that why we are not writing the this thing X and Y equal to the stoichiometric coefficient. The reason is that, like before I start with the reason, you should know actually like we should learn about reaction mechanism first, right? So before we start with reaction mechanism, we should know that for a reaction to occur, like in this the reactants are A and B and product is C and D. So for the reaction to occur, A and B must collide with each other, right? They must collide, they should bang with each other, and they should give rise to the product. So this should happen, right? So that means you know that the reaction which appears to occur in one step occurs in many steps. So we have two kind of reactions. One is the elementary reaction, other is the complex reaction. Now what is the difference between the elementary reaction and the complex reaction? The reaction which occurs in one step, the reaction which is a simple reaction which is occurring in the one step, is called as elementary reaction. For example, if I say I react A and B, and these are two you can say reactants, they are colliding and they are giving rise to product, and this is happening in one step, so it is considered to be in an elementary reaction. But if the reaction appears to be occurring in many steps, for example, if I say, suppose I have this reaction A plus B in presence of catalyst, suppose AB. You know that like I have written this reaction in one step, but actually it doesn't occur in one step, it occurs in series of steps. Now what are those series of steps? Actually this catalyst react with one of the reactant to form reactant intermediate, and then this intermediate react with the other reactant, giving rise to product, and along with that we get a catalyst, right? See, so what happens, like I wrote this reaction in a single step, but actually is it occurring in a single step? No, it is not occurring in a single step, because when we get to know about its mechanism, it is occurring in a series of steps. So as in this example, it is occurring in two steps, so that means we have two different kind of reactions. One is that in which the reaction occur in one step, that is our elementary reaction, and a reaction in, or you can say a complex reaction in which the reaction is occurring in multi steps, right? So we have these two different kinds of reaction, elementary and complementary complex reaction. Now what happens, like when we are considering the elementary reaction, so the total rate of the reaction depend upon this one step, right? And when we consider this complex reaction, the rate of reaction will depend upon many steps, because it includes the many steps, right? So it is depending upon different types of steps, as it is occurring in many steps. So before I tell you that like in one step reaction or in multi-step reaction, rate of reaction is determined by which step, I want that you should know that a new term, that is the molecularity. Right. Now what is the molecularity, and why we are studying it? As I told you that for a reaction to happen, A, B must collide with each other, they should bang with each other, then only they will give rise to product, you know that. So that means like in this reaction, how many reactants are colliding? 2 reactants are colliding, right? And likewise, I can have this reaction, I have shown this reaction A, B, C. So how many reactants are combining here? How many reactants are colliding with each other? So these are 3. So that means depending upon the reaction, or you can say depending upon the number of the reactant species which are colliding among themselves to form product, that indicates the molecularity. Like I'll explain you with example. Suppose I have 3 reactants, right? For a reaction to occur, these 3 reactants must collide with each other. They should bang with each other. Then only they will give rise to product. And if somebody asks you about that, what is the molecularity of this reaction, I'll write A. We'll consider 3 reactants A, B, C. So they are just coming to closer to each other, and they are just getting explored. You can say a type of bang is occurring between them because they are colliding with each other, and they are just giving rise to product, right? So if somebody asks you about molecularity, if I ask you about molecularity of this reaction, so I just simply mean by saying molecularity that how many number of reactant species are colliding among themselves. So how many reactant do you get to see in this that they are reacting? So obviously these are 3 reactants which are colliding with each other. So that means the molecularity is 3. So this is how you just like by just looking at the number of the reactants which are colliding among themselves, we get to know about the molecularity of the reaction. And you know, like we have different types of reaction depending upon molecularity. We have unimolecular reaction, in which, for example, I have this thing, breakdown of ammonium nitrate. You know, when ammonium nitrate collide with itself only. There is no other reactant involved. So that means it is unimolecular, right? And when it breaks down, it forms ammonia and water, right? So in this reaction, what we get to see that this is only one reactant which is colliding with itself, and because the reactant is one which is colliding with itself, that is why it is considered as unimolecular reaction, because the number of reactant species in this given reaction is only 1. And we have one more this thing, molecularity extend up to, it is bimolecular reaction also. So bimolecular, bi means 2. So that means in bimolecular reaction, how many reactant molecules you will get to see colliding with each other? Obviously we will get to see 2 molecules. For example, I have this. See, this is colliding with this. So how many reactant species are colliding among themselves? Obviously 2. So that is why it is considered as bimolecular reaction. And we can have trimolecular as well. Trimolecular is that in which you get to see, suppose I consider a general example, A plus 2B give rise to AB2. So we are not concerned with the moles of the product in molecularity, keep in mind. We are just concerned with the number of the reactant species which are colliding with each other. So how many reactant species do you get to see on this side? Obviously 1A and 2B, so that means 2 plus 1, 3. So that is why it is considered to be trimolecular reaction. So if somebody asks you about molecularity, by asking molecularity, he simply means that how many reactant molecules do you get to see colliding with each other. So if you get to see 1 with itself, then it is unimolecular. If you get to see 2 reactant colliding with each other, then it is bimolecular. And if you get to see 3 reactants colliding with each other, it is trimolecular. See, we do not get reaction more than trimolecular, because when the reactant exceeds 3, then the reaction actually occur in multi-steps, right? So we get to see, like if on the basis of molecularity we are talking, we get to see only reaction commonly occurring reaction only up to trimolecular reaction. Now you must be thinking why I am explaining you this new term, because we were talking about the reaction mechanism, and I told you that the reason behind we were talking about reaction mechanism is that what is the reason that this X and Y is not equal to A and B, and in many cases it appears to be equal to A and B, right? So I am just going to link all those things. Just look at the board again. We are concerned with the topic that why X and Y is not equal to A and B sometimes, and sometimes it is equal to A and B, right? Then how we will get to know that, in which case we will be using the stoichiometric coefficient, or in which case we are going to use the experimental values, right? So our concern is this. Right, but before I want to explain you this. Before explaining this, I just want you to know that for a reaction to occur, there is you can say a compulsory thing that has to be happen. That is the collision between the reactants, and depending upon the number of reactant species colliding, we have different molecularities, right? And as I told you, we have a reaction which occur in one step and we have a reaction which occur in many steps. So that means in case of elementary reaction, that means in case of simple reaction, if we are talking about the rate, it depends only upon the reactant involved in the single step, as it is involving only a single step reaction. But when we are talking about the complex reaction, so we have series of steps, right? So that means on which step our rate of reaction is going to depend. Right. So the reason behind that, you know, that I told you molecularity just to make you familiar that in case of complex reaction, the rate of reaction is just going to be different for different steps. I repeat, as the complex reaction is occurring in different steps, the rate of reaction is going to be different for different steps. As the rate is going to be different, so obviously molecularity is going to be different. And as the molecularity is going to be different, so obviously the order is going to be different, and that is why we are getting different X and different Y in some cases, right? Suppose I explain you with one example. Suppose if I say this, like if I take this reaction and I tell you that this reaction doesn't occur in a one step, as like it is assumed that this reaction occurs in many steps. Suppose I say that this reaction occurs in 6 steps, right? So out of these 6 steps, suppose this 4-1 is the slowest step. Suppose I say this 4-1 is the slowest step. So that slowest step is something called as rate determining step. That means, as we know that different steps are going to have the different molecularity, different order, and they will affect the different like the effect on the rate is going to be different. So suppose it is occurring in 6 steps, and out of those 6 steps, the 4th step is the slowest step, right? So that slowest step, like out of all the steps, the step which is the slowest of all is considered as rate determining step, and that step is considered to be you can say to know the molecularity of the reaction or to know the order of the reaction. For example, I explain you with one more example. Suppose I have KClO3 plus FeSO4 plus H2SO4. So what product you are going to get? Obviously KCl, Fe2SO4 whole thrice, and we will be getting water along. And if we balance it, we get 6 moles, we get 3 moles, we get 3 moles, and we get 3 moles. Like, if I ask you about the molecularity of this reaction which I wrote, so how many reactants do you get to see in this? So obviously it has 6 reactant, 3 of this and 1 of this. So that means 6 plus 3 plus 1 is going to be 10. So that means it is involving 10 reactant molecules. So do you think that this reaction is elementary reaction or a complex reaction? So do you think that these 10 reactant molecules can collide at the same time? No, they cannot, right? So that means this reaction is not an elementary reaction, it is a complex reaction. That means it is occurring in many steps, right? So it is confirmed that this is multi-step reaction, right? And as I told you that if the reaction has different steps, right, then the rate of the reaction depends upon the molecularity, which indicates the order of the rate determining step. And what is that rate determining step? That is the slowest step, right? So that means we'll be writing a mechanism involved in this reaction, and because they are not, the 10 reactant molecules are not going to collide at the same time, they will be colliding at different steps, and each step will have the different rate, and the slowest step is considered to be rate determining step, which will indicate the molecularity of the reaction for the whole reaction, and that will give the order for the reaction. Suppose, like if I talk about this reaction, you know what is the order of this reaction? It is the second order reaction, because the slowest step of this reaction, the molecularity is 2, therefore the order is 2. So that means in a multi-step reaction, we are just going to consider different steps, and the step which is the slowest of all, as see again I am telling you one thing, suppose this reaction occurs in many steps, right? So many different steps are going to possess different rate, and all the steps are going to possess different molecularity, and as the molecularity is different, that means the order is going to be different, right? But when I want to know about about the order for the whole reaction, I am just going to consider that step that is the slowest of all, because that step is something called as rate determining step, and the molecularity and the order of the reaction is suggested by that rate determining step. And like if you are a little confused about rate determining step, I am just going to give you one practical example. Suppose if I say that suppose I am traveling to Delhi, right? I am traveling from Chandigarh to Delhi. So like we know that the highways and all, we have the highways which are built already. So we face like we don't face a huge kind of traffic, and we can just increase our speed and go to Delhi, right? But what happens when we just cross from Chandigarh to Panchkula, and we are going from Panchkula to this thing Ambala, there is you can say a certain piece of land where the highway is being constructed, that is in Bravais, right? So what you get to see that in Bravais, that there is a small patch of land where the traffic you can say just gets stopped, because that road is too narrow. Due to the construction, that road is too narrow. So that means all the traffic just lined up, because only the few cars can pass through that passage, right? So suppose if we say that when we go from Panchkula, like leave Delhi, Delhi is too far, take the route from Panchkula to Ambala, right? So when we are going from Panchkula to Ambala, there is a patch of land in Bravais where the bridge is being constructed. So at that the patch of land, there is a narrow road, so that means only few cars can pass at that time, right? And sometimes traffic is too high that all cars just get lined up. So that means if the total time which is taken by a passenger from Panchkula to Ambala is 20 minutes, but if there is a traffic in that patch, that means we are not going to reach Ambala in that given 20 minutes. That means we are going to be like our time is going to be more than 20 minutes. Then what is the factor that your time is getting increased? That is indicated by the traffic which you face when you going through that patch of land. So that the narrow road, which is I told you is in Bravais, is the rate determining step, because that is the slowest step we are facing, because we are getting late only due to that patch of land, right? So that is considered as rate determining step. So similarly here, when we have the different steps of reaction, then out of that the step which is the slowest of all is going to indicate the rate. It is called as rate determining step, and it is the step which is just going to determine the rate of the reaction. That means it will show the molecularity and is going to determine the order for the reaction, right? I think it's clear that why I told you that the molecularity or the reaction mechanism, and how it is linked with the multi-step reactions, or what is the rate determining step. I am going to explain you with few examples, taking into consideration the mechanism as well. Suppose I have this reaction NO2 plus CO give rise to NO plus CO2. Right, I have this reaction in which NO2 is combining with CO and it is giving rise to NO plus CO2. So this reaction appears to be elementary. You must be thinking that because I wrote in a single step, so that means you must be considering that it is a single step reaction. But it is not a single step reaction, it is a complex reaction because it occurs in two steps. Now what are those two steps? See, we are going to do a mechanism for this reaction. So what happens? This NO2 first combines with the O2, sorry, it combines with NO2 again. NO2 is going to combine with itself and will form NO3. Then this NO3 is going to combine with CO, the other reactant, and it is going to produce NO plus CO2. So that means if we talk about mechanism of this reaction, it is occurring in two steps. In one step, NO2 is combining with itself to form NO3, and then this NO3 is capable of combining with the other reactant, carbon monoxide, giving rise to nitric oxide and carbon dioxide, right? So these are the two steps. Now if we just want to know the rate of the reaction, right, we should know that out of them which reaction is going to be fast and which reaction is going to be slow. So in this two reactions, you know that this is considered to be a slow reaction, and as compared to it, it is a fast reaction. We are not concerned with the fast reaction, you know that we are not considered with the fast step. We are considered with our slowest step, and that is going to be rate determining step. So out of this, which is going to be rate determining step? Obviously this one. Right, so that means our rate depends upon this step, that is the first one in which NO2 is combining with NO2 to form NO3. So that means if I am going to write the rate, I will be going to write in this way rate is equal to rate constant, concentration of NO2, because these are two reactant molecules, that means molecularity is 2, which will indicate the order for the reaction. So that means it is considered to be second order reaction. See, so when as I told you about the result that it is a second order reaction, so see what like if we look for this principal reaction, we have NO2, CO, NO and CO2. So when we are talking about the differential rate law, you must be thinking that the rate of reaction depends upon this NO2 and this CO, right? As you can see, there is 1, so you will write that NO2 raised to power 1, CO raised to power 1. That means molecularity is going to be 2, right? But it is not like that. As you can see, the rate just depend upon NO2. It is independent of this concentration of carbon monoxide. So I think it's clear that it is not always that what is written in a reaction is going to be you can say is going to affect the rate. It may be different sometimes and it can be same sometimes. So as I think it's clear that we'll be writing the mechanism first for the multi-step reaction, then we'll indicating the slow and the fast one, and then we'll write the rate, and the rate is going to be affected by the rate determining step, that is slowest of all. So out of this, so we have 2 molecularity, that is why I wrote NO2 raised to power 2. So I am giving you, so it is a second order reaction. Now we are going to start with the second